Take. Good evening. My name is Asif. I'm a tech biz dev manager for containers, and I'm a hobby coder at night these days. But the idea behind this session is to talk about machine learning and how do we deploy machine learning applications on containers. This is a blog. The first part of the session would be a blog that I built, and we published this last year in January about how do you do this. I've also got with me Hokuto and Yoshiro from Cookpad, who's going to talk about how do they use machine learning to power Cookpad on containers. So thank you for coming in so late. It really shows that you care about the topic, so that's awesome. So let's get started. What we're going to cover in the next 45 minutes and then open up for Q&A is what is deep learning? Why should we care about deep learning? When we say deep learning, it's a pretty loaded term. Data scientists train the models, but how do we apply this? And where is machine learning today in our lives? And then we'll look at a reference architecture of how do you deploy deep learning functions on Amazon ECS and what ECS does. And then we'll go deep into the Cookpad usage. So let's get started. Machine learning has been in our life in different formats for the last couple of decades, maybe or more. Like the term machine learning was coined probably in the 50s, the first time it was coined. But the idea is we have all learned math in school. We've done linear regression, logistic regression, and those need compute to run. As the cloud evolved in the last 10 years, it made very easy to run compute cycles. So when you run deep learning functions on the artificial intelligence side of the house, you need compute power because you're running n number of cycles, and n is a very large number. Deep learning is a branch of artificial intelligence, and it has 4 broad categories. The first being image recognition. So when we walk into a JetBlue kiosk, and I can check in with my face. And how many of us have actually seen it or checked in with our face at JetBlue kiosks? Okay, nobody? Cool. But when you go, it's okay, that's always a good question. So it's fascinating that you can walk up to a kiosk and stand there and it knows you, and it checks you and prints a boarding pass for you. Similarly, let me ask a simpler question. How many of us go through Clear at airports? Some? Good. I go through Clear. It's super easy because they have my biometric identity and I can go through. And Clear is a different biometric identification, but JetBlue is more of a machine learning part. Then we have natural language processing, which is basically speech to text, text to speech. When you look at Alexa, when your home assistant's at home, you can talk to them. I can send a text to my son from a plane or from like an airport, and Alexa or the Echo transcribes it and reads it back to my son, which is an amazing experience I have because my life or my interaction with my son has elevated miles away, where I have a busy lifestyle, so I could communicate in a different fashion. And the other classification is autonomous car, autonomy, autonomous robots, autonomous driving, and things like that. So that's primarily where deep learning is today, and many more algorithms are getting made. So I gave you a couple of examples why machine learning is important, or why deep learning, where is deep learning? Let's look at a couple more. So when we are shopping on websites for clothing, there's machine learning or deep learning being used to give us better options, to identify our needs so that we don't waste cycles browsing through catalogs and finding random items. That's one thing. Amazon Go is another novel concept where it's a cashless grocery shop where you can actually go in, pick up your item, and walk out without a queue, and you get a bill on your Amazon app. That is user experience. And and I've tried this at ghost shops, is you pick up stuff, you pick down stuff, and amazingly, the bill that I get is always correct. And that's a lot of deep learning being used behind the scene. But building deep learning apps is still an art. And when I say art, I mean there's a lot of magic that you need to build or invent. We want, with this talk and the blogs we published and what we are doing in the AI and the container space, it has to become a science. It has to become repeatable. And everybody should be able to deploy machine learning algorithms into their apps. So when I go to Zillow, for example, as an example, I look at the home estimate. As a user, I want to look at the home estimate. I don't want to look at the details. I want that clean experience. But I also want the home estimate to be correct or within an error margin. So when you look at that, there's a bunch of scientists at the back end who are developing data models, data crunching, to make sure the predictions are correct and give us those models that could be used. So that's the line, the horizontal line, the diagonal line below that the machine learning data scientists sit there and they crunch numbers and they do fabulous mathematic pieces and they come up with algorithms. But for an end user like me, to find the estimate of a home, for example, it's super important for me the experience is clean, this experience is seamless. So there's a team sitting there, which is DevOps, which is tasked with taking these data models, applications, and moving into production. There's another set of developers, which is app developers, mobile front-end developers, back-end developers, and they worry about how do I give the best experience to my customer, how do I scale this application, when I have a spike from 0 to 10 million requests on that API doesn't fall down. Those are very valid concerns, and you need to give that experience back to your end user for him to stay with these things. With that, let's go into how would you build such a solution that is working in harmony, using really advanced, complex algorithms, giving you great predictive results, but at the same time having an experience which is seamless and which can be deployed very rapidly. So with Amazon AI portfolio of services, you get multiple layers of services. If I'm developing a machine learning application, and if I have the prowess, I might go in the engine level and write code in TensorFlow, build my own model, or MXNet, and things like that. But if I want to use something more abstracted at a platform level, I could go use Amazon EMR, SparkML, Spark, and things like that. That is for me if I want to go really deep and build stuff. But there are tons of use cases where the abstraction has to be an API call. I don't want to build that model. It's an image recognition problem, and Amazon Recognition has a vast data set trained, and if I try to build it, it will take me time. I'll get there, but it'll take me time. So I could use an API like Amazon Recognition and go with 8 different type of image classifications I get. I can even read text now. Like recently, Amazon Recognition announced that you can read text like license plates and things like that. Imagine the use cases it enables from just that text reading. The other primitive that I need to build my service is a container. Deploying one container is super easy. Docker did that. You can say Docker run on your laptop, and it works. But imagine deploying thousands of containers on thousands of nodes. So you're deploying M containers on N nodes. And you're trying to solve now an O of N squared problem, which is a really hard problem to solve, which is called cluster management. So at Amazon, we built Amazon Elastic Container Service, which basically is a cluster management engine where we know or we keep track of the state of your containers, what container is deployed where, what are the configurations for it, what are the parameters, how should it scale. All of that we put in the cluster management engine. We have an API that you can access this via. And we also have an agent communication service, which talks to the instances or the nodes where the containers are deployed. So the ECS agent, every instance that you launch has an ECS agent, which is my communication channel back to the cluster management service. I group a bunch of containers and call it a task. A task is a logical unit, which very roughly could translate to an app or a service, and I can scale it horizontally and say I want to run 100 copies of this app, and it just does it for me. I can front this with a load balancer. So if I have a spike, I need a shock absorber. I need to be able to take that 1 million requests per second and distribute it down to the containers and service those requests. So the load balancer gives you that. And it's a fully managed service that you do not have to do the cluster management. You just launch the cluster, and it works. One of the things that I always talk to developers about and we have a conversation is, this is not an easy problem. And as a developer, I don't care, only when the development platform does not break. Ask yourself, and how many of us have been in that situation in our development lives, when the platform breaks. That's a whole different emotion that we go through and what we come out with. But that's what Amazon ECS is built for: operational efficiency, deep integrations into the platform, security, logging, monitoring, all of that, all the goodness of the AWS platform that you are used to. So I talked about the AI engineer or the data scientist, what he uses. I talked about the DevOps and the application development part of it. But what about building a pipeline which releases super fast? If I have a new model, which I trained tonight, I want that model to be consumed tomorrow morning or maybe during the night to give me better predictions, kind of a continuous predictive model. And for that, we have a set of tools we call as developer tools, like Code Commit is a managed private Git repository. Code Pipeline is our pipeline tool, and Code Build is a managed build environment, and Code Deploy automates deployments. You can take these primitives and build your very custom or specific developer workflow. But let's say you're getting started, or you want a templatized approach. You can go CodeStar, and you can say, this is my app, do this for me, and it just does it. So enough of products and primitives that we needed to understand when we get it into how we are building this. So let's get into how to do this. So I'm a data scientist. I'm working on amazing algorithms. I have a large data set. I'm crunching. And I live on an EC2 instance, and I live in the Jupyter Notebook, which is pretty popular as a data science tool. I train my model continuously, and I run those models. And Amazon has open source or published armies that you can just click, and it comes up with a Jupyter Notebook, so you do not have to install it. But that's where I live. And I might be uploading my models, which is basically the templates that get generated, into Amazon S3, which is a durable, scalable data store, because I want my models not to get lost or not to get deleted and things like that. As an application developer, my life is I want to write code on my laptop, on my local environment, and push this code to a code repository. Package it, push it, write the Docker file, and push it. That's where, that's nirvana for me. And magically, the app should use it. I also have a mobile client, so I have mobile developers who needs to use it. But to make this all real, I need a container management solution, a platform that scales, that I can deploy my applications to, the compute where I can run. So what you see on this box that came out, Amazon ECS clusters are provisioned. When you say create cluster, you can provision those clusters, put them on auto scaling. You can have different type of instances, on-demand instances, spot instances. You can front it with an application load balancer, which I talked about, which is a shock absorber kind of a deal. And you can put a DNS in front, which gives you a friendly name. And I also have a private image repository that I can use to store my Docker images. I don't want my images to be stored on a public repo. I want them to be controlled in a secure environment. I also want to log all my metrics and logs into CloudWatch, because monitoring and logging is super important for me. Now, all of this, you can go through the first run experience and create this as you go, or download a CloudFormation template from GitHub. We have open sourced a bunch of projects, and deploy this. There's also the DevOps part, the ops part of this, which basically is worried about creating the cluster, which we went into details about, but also building a fast release cycle, which is how do I build my pipeline so my developers can push code and it gets deployed by the second or the minute, build it in a scalable way so that I'm not running build servers on my side and spending money for idle time. So if I've done this right, what I do is I upload my model into Amazon S3. On the app side, I write a Docker file, which I kind of extend from MXNet, and I do my own Python app that I can inject in and basically say Docker copy, run, and entry point SH and things, and I build that image on a build server like code build, and I push that image into a repository like Amazon ECR. That's the happy path of the workflow. The CloudFormation provisioned my cluster, my application developer pushed his code, and my DevOps has built a pipeline which gets triggered. Every time code is committed, a pipeline is triggered, and the pipeline does build, and from the build environment, I can push code to Amazon ECR. One of the things I love about code build as a developer is I can script things into it. I can have a pre-command, a build stage, and a post-build stage. And what I can do is I can call other APIs. I can call an image scanning API. In this case, I'm calling an ECS API, an ECR API, which is Docker push, right from my build script. So what does this look at the end of the day? So on the mobile developer side, I'm calling an API. That's all I'm calling. I'm calling myproduct.com/predict. And what I'm trying to do here is I'm trying to predict what is this picture that this guy is taking or is standing in front of, and so that I can give him valuable deals or maybe give some facts around it. And I've used my machine learning algorithm to predict with, say, like in this case, around 11% probability that it's the suspension bridge. That's valuable information to know from a mobile app experience that I'm near the Golden Gate Bridge, and then you can build many experiences around it. So that's the happy path. I've uploaded my model is getting consumed my code. What if, let's talk about, tonight I ran a new prediction algorithm or training algorithm, and I have a new model. That model gets uploaded to S3, and the change is, literally, let me go back, is your code reading the new model from S3. MXNet has APIs for S3, and you can go TensorFlow and other things. For your code can read the new model. And if you have a new application perspective, you can go through the same pipeline and trigger it and deploy that on ECR in a rolling fashion like 1, 2, 3, 4, and all your applications or containers scale with the same image. So you've made it a repeatable process to deploy AI-enabled applications. And I also believe that today a big barrier of communication is the language. A data scientist speaks a different language than a DevOps engineer versus an app developer. We could use S3 as that communication model or the communication hub where I can read the model and let my code do the translation for me. I read a new model using MXNet API, it understands the model, and it moves on. You still need to talk to the data scientist, you still need to talk to DevOps engineer, people have to collaborate to make it happen, but your code can interpret models and the pipeline in a much more efficient manner, and what you end up with is this fast, efficient lifecycle of your AI-enabled application on containers that you can release by the hour, if possible, or even shorter. I talked, and when I push this new code, let me go back. When I push this new model and I've changed my code, and I want to update the service, I want to say, okay, I've written a new feature, released a new feature which uses this new model. All I do is call the update service API on ECS. What it does is it takes the new image that was formed or built, and it deploys it on all the containers. And it scales it to the number of tasks that you wanted, and based on your spike of your traffic as you go. Now, going back 5 years from now, before this, all this was really black magic to me, personally. But today, machine learning is a part of our lives, deep learning is a part of our lives, and I am an optimist. I believe deep learning will make our lives better as we go, and will help us do those things that we wanted to do, because we have spare brain cycles that we can spend on them. And I've discussed this at length with many of my friends. I would like to invite you to give it a spin. This is a blog which is published. A bunch of customers have used it. There's a QR code which makes it a little easier to go there. And this reference in the blog, you will also find a reference architecture. The whole code is open sourced. The CloudFormation template, the app, and all of it. Give it a spin, launch it in your AWS account, and see if you can build AI-based applications and put AI into the applications you have. With that, I would like to invite Hokuto from Cookpad to talk about what did Cookpad do for machine learning on containers. So I'll switch over to Hokuto.
Thank you, Steve. Hello. Thanks for coming to our session. My name is Hokuto Hoshi. I'm the head of the infrastructure at Cookpad and responsible for site reliability engineering. Today, we are going to share the story of how we built the containerized machine learning workload on AWS. How many of you know Cookpad? Okay, yeah. First, let me introduce our company. Do you like cooking? Do you like cooking? Cookpad is an online recipe sharing and search service. We are based in Japan and were founded in 1998. Since 1998, Cookpad has been providing online recipe sharing and search services. Our corporate mission is make everyday cooking fun, and our services currently hosts over 2.7 million user-generated recipes, and with about 60 million users in Japan visiting us each month. It is the largest online recipe sharing and search service in Japan. And we are global. We are operating in 67 countries and support 21 languages. For the United States, you can access our service at cookpad.com/US. We have offices in Japan and UK and Spain, Indonesia, and so on. We have about 150 developers to host the services, with 9 SREs and 9 machine learning engineers to support. We have been running all systems on AWS since 2011. We are using ECS for our service, and we run over 200 ECS services. Now, let us explain cooking log, in Japanese, 料理記録, which is our first deep learning product feature. Have you taken photos when you cook? Some people take photos of what they cook and eat to record and look back on the memories. That is to monitor their dietary habit or to share them with family and friends and communities. However, sometimes it is troublesome to find such food photos from your smartphone camera roll manually. In order to make that process easier, we developed Cooking Log, which automatically finds food photos from your camera roll. It is powered by convolutional neural network, which is one of the logics for machine learning. So let's watch a demo video of this feature. This is a video of Android smartphone. As we can see, there are many kinds of photos in the camera roll. There are some food photos. However, there are also other kinds of photos like aquarium and flower and scenery and so on. Yeah, like this. Yeah, this is nimono, which is one of my favorite Japanese foods. People who want to keep a record of their dishes launch the CookFat app and select the cooking log. So, loading photos from camera roll. Yeah. As we just saw, the food photos were automatically uploaded and archived. This is a feature. This feature is now used by many users. Today, over 140,000 users have stored over 12 million food photos. Let me introduce this feature from the technical side. It is our first feature that is using deep learning. So there were some challenges. It was the first time for us to run a semi-real-time image classification with production, and that workload was different from common web applications. What we especially needed in developing such features was the scalable infrastructure for new workloads and isolated environments for new challenges. We built it using AWS and containers. I will explain what scalable infrastructure is first. We needed a scalable infrastructure that enabled massive photo uploading and semi-real-time image classification. Because clients send a lot of tiny thumbnails every time they take photos. This traffic is difficult to predict. There was also the possibility that traffic could spike when this feature was introduced on television. For better user experience, we have to keep this feature at a constant performance at all times. So we choose asynchronous architecture. Uploading and classification takes a few milliseconds or longer, and it sometimes blocks our application processing that was written by Ruby on Rails. We decided to use the pre-signed URL of Amazon S3 and upload the image directly from the client to S3. Also, we enabled S3 notification. It adds requests of classification for uploaded thumbnails to SQS queue. In order to carry out deep learning in production, isolation of the environment was also necessary. Image classification software was written using a different language than we used, and it has a different workload from web application. Finally, in many cases, software for deep learning demands GPUs. This is a clearly different point from the web application that we have developed in the past. So we decided to create such an environment in a container. Containers can isolate a new language environment and GPU driver and various settings. We run this container on ECS with G2 extra large instances. In addition, Amazon ECS provides a managed and scalable Docker environment, which makes it easy to scale. Also, we have already run a lot of containers on ECS. Let me introduce the architecture of this feature using figures. At first, the client requests our API server to issue a pre-signed URL of S3. The API generates and returns it to the client. Next, the client uploads a very small thumbnails to the S3 bucket. As I mentioned earlier, we enabled S3 notification. So the S3 enqueues the event to SQS when the image upload is completed. The image classification that is running on ECS requeues the event from SQS and downloads the thumbnail and classifies it. After that, results of classification are sent to the API server. The API server removes images that is not classified as food. This is my architecture. With direct upload to S3 and using SQS, we could build a scalable architecture without preparing an image upload server. Even if the amount of uploaded images increases, the image classification that is running on ECS scales out quickly, depending on the queue length of SQS. The API server only needs to issue the pre-signed URL of S3 at first, and then wait for classification results from ECS. So what is happening in the container? I will hand it off to Yuichiro, and he will explain the image classification in detail.
Is my mic on? Cool. Thanks, Hakuto. Hey. I'm going to take over the session, and then I'll talk about a bit more detail about what is happening inside the container. Well, I'm Yuichiro. Yeah, I'm so excited to be here on stage. I bought a new jacket for today. Then I've been working for Cookpad for 1.5 years, and I'm working as an engineer in research and our research and development division, which means that my specialty is that I'm in charge of making sure that our researchers can access our data or GPU computation environments easily and fast, concentrated on their creativities. This is, yeah, anyways. First, I'm going to explain what the actual task in the ECS cluster, ECS container, is actually doing from the aspect of containerization of machine learning. Well, as Hakuto explained before, the task, the things task doing is that task first gets the image from the S3, and also task will they cure the message from the SQS, and also the task first download the classifier, the model from the S3, and set it up, and the task also they cure the message from the SQS and download the image from the S3. Yeah, that's right. And the task next doing the actual image classification and send the result back to the API server. That's it. So what we need to develop is are basically two things to make the whole system work, which is the classifier, of course, and the Docker image, which actually doing the procedure I explained. And maybe as Asif explained, the classifier could be set up large files, so it's better to store it in S3, which is scalable, durable, capable of handling the large files. Yeah. And developers or researchers build their model, train it, and save it to the S3. That's the first thing to do. And the developer also needs to implement the task itself. Yeah. And also, when we use the ECS, we need a task definition, of course. Yeah. For the task, ECS task definitions, we like we liked it to make it easy to manage or easy to write also, so that each developer can write it for their own applications. And with that, communicating with SRE team, for example. There is an open source Ruby library called Hako, H-A-K-O, which is developed by one of our engineers. And we are utilizing it to write the task definition down by YAML format file and manage it on the version control systems. Yeah, on the right-hand side, you can see the one example of the Hako task definition file for ECS. Yeah, and I'm going to explain the reason why we don't directly call the ECS API, but instead we use Hako and call the ECS API indirectly. First of all, we needed to perform higher level operations on the ECS, like deploy the new version of the application or roll back it. And according to that, for example, the git commit hash or revision or whatever you want to refer when you decide which version to deploy or roll back. And we also have common or repetitive, common and repetitive operations like injecting security environment variables or maybe registering the service to our own local DNS, or we may use another proxy container. We may need another proxy container for logging. Those kind of the common and repetitive operation is frequently appears, right? And yeah, I think it's also I think in most cases each company or each team has this kind of operations, set of operations we need to perform every time deploy the new version of the application. Yeah, things like that. So for these reasons, we use Hako's functionality to perform deploying and rollback operations, and also making use of its pluggable script architecture, where we can trigger and arbitrary operations before or after deployment. And as a result, our process of deploying a new application or new version is very easy, so that each developer can do it without much communication with infra team. Now, we have a task implementation, and it's Docker image and the task definition file all set up. And now I'm going to be a little bit more detailed about the task itself, since those GPU-accelerated instances had much higher throughput of image classification compared to the other CPU instances in a similar price ranges. So that's the reason we decided to use GPU-accelerated instances for this workload. I'm talking about the inferences on production application. And we would show you some tips or practices from our experiences running GPU workloads on the ECS for a while. Well, first of all, to run GPU workloads on ECS, we first need to configure the dedicated AMI for the cluster, because NVIDIA driver of a GPU consists of user libraries such as shared object or kernel modules. which needed to be installed to the cluster, not in the container. Yeah. And because both kernel module and the user library are tightly bound, I mean, talking about the NVIDIA's driver, is tightly bound in their version. So it is better to install both kernel module and the user libraries together to the cluster, and not separately, together to the clusters. This is, yes. On the other hand, the things like a CUDA toolkit can be placed on the task. There's a kind of practice. Since it could be, CUDA toolkit, things like that could be changed in the version depending on the task. So that's better to store in the container, installed in the container. Yeah, this practice is well explained in NVIDIA's NVIDIA Docker documentation. Yeah, you can check that. And at last, in ECS, when we're using the container with the GPU, we need to set a privileged flag that would open the privileged access to the GPU device, right? And we need to set that flag. And actually, that was a situation at the time we first released this application. Now we have more detailed options like Linux parameters, devices options. So we are now kind of working on migrating from the privileged mode to Linux parameters options. All right. So now we have almost everything set up. I'm going to continue with detailed explanation on how we built food or non-food image classifier in our project. So I'm going to talk about the machine learning from now. Well, all right. So some of you may already know that image classification in the area of deep learning it may be said to be the solved problem, which means regarding to the result from the recent academic competitions, the models can distinguish things better than human. So it is true that we can build working classifier by just collect enough number of labeled data sets. This time food photos from cookpad and no food photos. No food photos is a random food from the open data set. Yeah, may include some food photos, but it's only a few. And then and we can just perform supervised learning using the labeled data set. The model could be one of those famous pre-trained model like Inception from Google or ResNet or VZZ, for example. Yeah, that sounds like working. But after we shipped out our first version of the classifier, we gradually got direct feedback from our users, which says that there is still notable number of non-food photos mistaken as food, which means that the user has the food plushes on the calendar. Yeah, we got this kind of feedback. And I'm going to be more detailed about the problem. The background of this problem is called open set problem, which means like limitation of the domain of the data set. Yeah, I have much things to discuss about it, but won't really go detail about it right now on the stage, so we can discuss about it later. And then let's say it's easy to construct a food data set. We can just collect the food photos. But for non-food, it's hard for us to construct the data set of every single thing other than foods, like cars, chairs, humans. And instead, it is the usual practice that we have only one level non-food, which is called open set here. And then put random photos into the data set, non-food data set. And let's say we have no photos of plushes in the data set, not specifically this photo, no plushes in the data set. The model could be checking about this, his answer when the model the model gets the photos of plushes, the model could be checking in his answer. So that is the background of the problem. And so what we did is by investigating the results from our local test set, hopefully we have the various things which looks like food. And we rebuilt the data set. We rebuilt the data set according to the investigation. More specifically, we put the brushes as a separated label, for example. Yeah. The thing is not that simple, but yeah. And we succeeded to increase the accuracy in our model. Yeah. 97.9% accurate. That's good. And all right. So I'm gonna move on to the next topic. As I introduced myself before, I'm an engineer in the research and development division. I've been interested in making it possible for our researchers, data scientists, do their work easier and faster. Now I'm going to talk about our infrastructure where we are doing using the AWS GPU instances for various experiments. Sorry. Let me move on. Sorry. Yes. Okay. So we are using the EC2's GPU accelerated instances like G23 or PT23 for our experiments on the data sciences, not only in the production, of course. And we wanted those instances on demand so that our researchers conduct their experiments in parallel. Multiple researchers can conduct the multiple experiments in parallel. That's the spec. And because of that, we make use of Amazon machine images to realize repeated provisioning of those commonly used components like GPU driver or CUDA toolkit or CUDNN maybe. And we are also making use of a chatbot on Slack as an interface where anyone in the channel can create, start, stop instances using those AMIs. Yeah. And one more thing here is using Packer by HashiCorp. We can automate the provisioning steps. As I said, installing the NVIDIA driver or CUDA toolkit, so that we can update the AMI fast and stable ways. Yeah, like this. And of course, there is a managed AMI for deep learning. Yeah, some of you may already know that the AWS has a managed AMI for the latest version of CUDA, for example. So, which is actually not available, was not available at the time we started using GPUs. So we are now, on the way to migrating from our in-house AMIs to managed AMIs. Anyways. Oh, all right, that's it. So I'm going to wrap up the session. We introduced the cooking log using deep learning at scale, adopted asynchronous and isolated architecture with ECS. Yeah, and we also make very great use of AWS's GPU accelerated instances for our experiments. All right. So, yeah, and we are hiring. Yeah, we have the two main offices in Japan and the UK, Bristol. Yeah, if you're interested in our, machine learning infrastructure, you can contact us. Yeah. Thank you.
Cool. Great. Cool. Yeah. Cool. Thank you, Hokuto Ichiro, for sharing the CookPad use case. Thank you for attending the session. We can take a few questions. I think we still have a few more minutes. We're counting down to 10 seconds, but I think I can take two more questions. Yeah. Yeah, so very good question. The question was, why did I choose, or why did CookPad choose a container management platform and not a serverless platform? So I'll answer it from the more architecture perspective, and Hokuto and Yuichiro can talk about why they chose it. So when you go to a serverless model, you have to live with good citizens rules, which is a number of CPUs that you get, number of memory you get. But with containers, you get the horsepower you need. So if your prediction algorithm or the prediction inference API is very lightweight and it can live within those boundaries, absolutely. But if your inference algorithm does a lot of things, it's an app, it has caching, it has done things, and it needs that high throughput and latency, like low latency, then containers kind of give you that edge. We have a reference architecture even for serverless published. If you want to try that, yeah, I know, you've seen that. So if you can try that. But what we've seen from customers is a lot of machine learning inferences are running on containers. We've also started seeing training running on containers, which is very early days right now. But a lot of training is still running on EC2s because training on containers is still like happening. And okay. Yeah, sure.
So the major problem we have seen is the allocation and a clustering algorithm. When we not have this project, it is pretty simple. When we try to generate the models, by the time we generate the models and deploy the models into the production environment, usually some hackers already changed the models. Because we are trying to do some phishing algorithm and trying to predict on phishing algorithm. So the hackers are involved trying to predict whether the sites are fished or not or something. By the time we generated our models using the classification and by the time the models are generated in the staging environment, we are training the models to work. And when we push those models to production, we are too late in the game. How do you solve that problem? That's what I want to ask.
Good question. So the question was really, how do you get from reduce the lag between training a model to deploying it? That's, in a sense, the question. So when you look at the architecture that CookPad showed and I walked you through, the whole idea is to build an efficient pipeline. And as the model is getting uploaded in S3, let's say tonight I ran a training algorithm and it got uploaded into S3, my code that is deployed is calling the MXNet API. MXNet is calling the S3 API, where I'm pulling the latest code from within the code. So I'm saying mxnet.get, and I'm always pulling the latest model. The model is not in the container. We are not caching the model. We are at runtime. I'm sitting in the same VPC. I'm not going outside the VPC. I have no internet connectivity if I choose to. And I can always get the latest model if I choose to. Or I can cache it if I want it to run even faster. So that problem kind of becomes non-existent if you have used the APIs correctly and you've built a really efficient deployment pipeline.
The reason is why I especially mentioned is the classification is I have predictors and I have target. That's the way the model you generate. But we work on some projects where we do a lot of things of predictive analytics on the hackers. Yeah. Hackers or whatever we do in our agencies, okay? The problem is by the time we send the model to the production, deploy to the production environment, the hacker or somebody already changed everything. So the algorithms are not working. So we're trying to figure it out how to solve that problem. So you train the model first time, right? Is there any way you can do dynamically train the model in the production itself? Especially that is the main problem. I was thinking deep learning can do something on that. And if you really look at a very sensitive projects, like not civilian projects, some other projects which we work on, those projects have those problems. I'm trying to understand how really you can solve that type of problem. That's why I said usually this classification algorithm, I'm talking about that. By the time you change something, the hacker already changes everything, and whatever we're trying to predict it's not valid. You know what I mean?
Yeah.
But because training is done not on the production data. So that's why there's a product called Apache Nifi. I don't know whether you know Apache Nifi or. It can stream the data into the engines and does the prediction on the fly.
Yeah.
That is what I'm trying to understand in the deep learning, how you guys are trying to do. But that's fine. Okay, I can ask you later on.
Yeah, we can take this offline, but to answer the question quickly, when you talk about lag, what we're really talking about, the lag between data and deploying the model. That's what we're talking about. It really depends on how you're pulling the model. Are you caching the model in containers at runtime in production? Are you pulling it?
The problem is the model. Okay, I will talk about
Yeah, we'll take offline. Any other questions I can take? Okay.
The assignment of tasks to individual workers within your cluster, is that handled by the Symphony service?
Do you want to take that question?
Sorry?
Can you repeat your question?
The assignment of individual images, thank you. The assignment of individual images to be classified by your model that is running inside of that cluster of GPU machines, is that assignment to an individual machine, is that handled by the SQS?
Well, you mean the images is a photos, right?
Yes.
Well, your question is, sorry, I didn't get it.
So if I can paraphrase, so when your images come on, like from the phone, upload to SQS, and you deploy it on the GPUs to train it, is that handled, the SQS pulling and training, also handled by the worker nodes?
Yeah,
that was
not for training, but for the production classification.
For the production classification. So I got a photo landing on S3.
Yes.
I have an SQS from where I pull the photo, and then I try to predict it or run the inference API.
Yes.
Does your worker node do that, or do you have that separately?
You mean the training and the inferences?
The inferences, yes.
Oh yeah, inferences. The worker is just working like worker continuously working as a process, and then the just purring for the SKS for the searching for the new message coming, and the classifier pull the image and the doing the inferences. Also reporting the results back to the API. All the things is doing in one set of implementation of the worker.
Okay. And how does it set to scale as demand ebbs and flows? Auto scaling groups?
The scale rules, you mean?
Yeah, so when you are uploading a lot of photos.
Yes.
So initially, let's say I upload 100 photos. So that has a SQS queue depth and scaling. But supposedly, my app is used by 100,000 users, and now I'm getting a lot more photos.
Yep.
How do you handle the scaling? How do you trigger it? And what does ECS do, or how do you scale that containers?
Oh yeah, the scale trigger is basically there is one matrix on the SQS is what is called the approximate max age of the message, and then we use that to making sure that we won't get the message waiting longer than the thresholds.
Okay, thank you. Last question, have you considered Amazon Batch for this kind of workload?
That's a good question.
So if I can take that, right? So Amazon Batch is a service which runs with ECS under the hood, right? It has a queuing mechanism and all of that. So the batch construct is a HPC construct, and you can use batch absolutely. But sometimes for batch jobs, you need lower level control. And I do know of customers who are trying to use batch, but as Cookpad, Yuchuro talked about, when they started the journey, probably AWS batch was not there. So they made the decisions. And running batch jobs on your own is absolutely fine, because you might have certain semantics and constructs that you would want to control. But with AWS batch, you can totally run those API, those repeatable jobs if they fit your need. So I would go back to say, what am I running as a batch job? Look at it if that solves the problem from an abstraction perspective, and then make the decision. Does that make sense? Cool.
Yeah, and the huge difference between the AWS and the ECS and the batch is that we need the application perform semi-real-time inferences. We need to make sure that the message is waited no longer than the thresholds. The batch is kind of, the waiting for the tons of tasks and perform the inferences at scale. It's a bit, there's a bit gap between the architectures.
Absolutely. Any other questions? We can take this and then go there. Oh.
A bit out of scope, but how do you manage intercontinental and intracontinental regulations if you're processing on the server side? Do you have any kind of pre-processing within a particular region before you even transfer the photo outside?
Well, you mean the variation between the input from the different?
So your source could potentially be from the U.S. Your region could potentially be outside of your cluster could be outside of the U.S. Do you have any kind of pre-processing within a local region prior to actually?
Well, actually, we have the two separate systems for the image classification in Japan and the image classification outside of Japan. Yeah, we had only those two, basically the version of the model, and then we don't care so much about the variation between the countries of the continent about the kind of input we get. So yeah.
Yeah. Does that answer your question?
Well, it's more of a, well, let's just say that images that could be legal in the U.S. may not be legal in, say, Europe.
Yeah.
So the question is whether or not you can stop those images prior to transfer to Europe.
Wow.
Yeah, that's a good question. It almost borders on the line of data residency, data processing, local residency. I'd love to talk more to you offline about that. So absolutely. And I think there was one more question here.
Can you speak to your CI/CD pipeline? Do you use code start, code build?
Yeah.
Well, you mean the deployment pipeline?
Deployment pipeline.
Yeah, well, the whole development pipeline from code commit to code build and deploy, the whole process. Do you use any tools?
Oh yeah, you mean the deployment of a new version of the model, maybe?
Yeah.
Oh yeah, we use we of course use the CI and the CI which does the building the Docker image, and also we can have we can make use of the rundeck. We can fire the any kind of scripts we're using for the deployment of a rollbacking. So we just searching for our jobs and click to deploy, and then we will get the new version of the model.
Totally. Thank you so much for coming. We are like 3 minutes over time, but thank you for coming. I will hopefully learn something. Thank you.